Okay, so we are now ready to define trigonometric functions for the kind of angles that we have defined, that is rotational angles. Now, before we do so though, we need to know what it means to put an angle in the standard position. You can already see that I have drawn a circle here and there are coordinate axes so that the circle's center coincides with the origin of this coordinate system. This is our usual x-axis, this is the usual y-axis. And the circle, besides having its center at the origin, is also of radius 1. That means it's a unit circle. And that is why these points where the circles intersects the axis are, each one of them is at unit distance from the origin. As such, these are the coordinates of these points, okay, which are easy to see why they are so. For example, since this point A lies to the right of the origin and on the x-axis, its coordinates are 1 and 0. X coordinate is 1, y coordinate is 0. Similarly, the other points also have their coordinates. Now, say you have an angle. We know what an angle means. A rotational angle consists of an initial ray, which also is called an initial line, the initial line of the angle, and another ray which rotates either clockwise or anti-clockwise in such a way that the initial point of that ray, which is this one, is the same as the initial point of this fixed ray, and that ray is called the terminal ray or the terminal line of the angle. So the angle which corresponds to some kind of rotation has its terminal side or terminal ray looking like this. Say the rotation is something like this or like this, but whatever the situation is, that is the position of the terminal ray. Now this is an angle, okay, this figure is an angle, and each such figure comes with an angular measurement which we also call an angle. Now, when do we say that the angle is in standard position? Okay, to make this more clear, this is the initial site or initial line, and this is the terminal line. To put an angle in the standard position, first of all you have to choose a coordinate system. That means you have to have an x-axis and a y-axis. Then you take the angle and adjust it in such a way that the initial line corresponds with the positive, it coincides with the positive x-axis. Okay, so that initial line now becomes this ray. The positive x-axis is also, after all, a ray, and accordingly the terminal line will also get some position. Say this one. Okay. So initial line always coincides with the positive x-axis, and the terminal line, depending on what it is, it will take some position. Whatever position it takes, it will intersect this circle at some point. In this case, that point is this point P. Say with the coordinates A and B. Okay. Now, say the angular measurement of this angle is x radians, or theta degree. We can either use radian or we can use degree. usually we will use radians more because we will be using radians mainly in calculus. That's why we need to get used to radians. And as per the convention we are following, when we write the radian measure of an angle, we do not normally write radian. So we just simply say that the angle is x. It means it is x radian. So that x is associated with this rotational angle, however the rotation happens. Alright, now this is the situation. Now what will be cos x and sin x? Let us now define that. Now we will say what cos x means and what sin x means for this rotational angle x or theta degree. I mean, any angle that is in radian, you can convert it into degree, it's not a big matter. So the definition is this: cos x is defined to be equal to a and sin x is defined to be equal to b. That's what they mean. That is their meaning. So if someone asks you what is cos x, say someone gives you a rotational angle and that angle comes with an angular measure x radian, and someone asks you, okay, tell me what is cos x. So what will you do? First you will put the angle in the standard position. What is that? In that standard position, the angle's initial line should coincide with the positive x-axis, and then the terminal line will lie somewhere, and that terminal line will intersect the unit circle, this unit circle whose center is at the origin at some point P. The x coordinate of that point is defined to be cos x. That's what cos x means. And the y coordinate of that point is defined to be sin x. This is the meaning of cos x and sin x. Now at first it seems to be something entirely different from what we know about cos x and sin x. I mean, this is not how we define cos x and sin x in lower classes. For example, cos x for us is something else. Base divided by hypotenuse of a right angle triangle, that's how we know cos x. Similarly, sin x is altitude divided by hypotenuse. But you have to keep in mind that now x is no longer necessarily an acute angle. X can be negative also because x is related to rotation. So the definition is also different. However, we will soon see that in spite of this apparently different nature of this new definition, if x is acute, we will get back our old cos x and sin x. Let us, however, see some new things here. What is the implication of this definition? We can immediately say something about cos x and sin x just from this definition. Let's see what that thing is. You already know how to calculate the distance between 2 points in a plane whose coordinates are given, right? You already know about the distance formula. Say you have 2 points P x1, y1 and Q x2, y2. Do not confuse this P with this P, okay? This is some point P. Then the distance between P and Q is given by this. Square root of the sum of these squares of coordinate differences. This formula itself comes from Pythagoras theorem. Okay, we do need that thing from geometry to derive this formula. Now we can use this formula to calculate the distance between P and O. Actually, it's a special case of that formula. In this case, that distance will be what? a minus 0 whole square plus b minus 0 whole square. In other words, that distance is the square root of a square plus b square. However, that distance is actually what? That is the nothing but the radius of the circle, which is 1. Okay, so that means we have this, which implies what? If you take square on both sides, you will get a square plus b square equal to 1. But here a is cos theta and cos x and b is sin x. So that's how you get cos square x plus sin square x equal to 1. Even in this general setup and even in this new definition. So we obviously are not going to write all these things. This was only for our understanding. Instead, we will write, after defining those things, this. Since a square plus b square is equal to 1, we have cos square x plus sin square x equal to 1 for any real number x. X radian, that just simply means x. So at least one thing from before is still true. Many other things will turn out to also be true. Alright. So let us now put this new definition to finding out some actual numerical values for some specific angles for the cosine and sine function. The first easiest angles that you can think of are quadrantal angles. What are quadrantal angles? A quadrantal angle when in standard position Okay, a quadrantal angle when in standard position, that means when the angle's initial line is the positive x-axis, has its terminal line on the x-axis or y-axis. Such an angle is called a quadrantal angle. One easy example is the angle whose initial line of course is this, and the terminal line is also this, same ray. And the angular measure of that angle is 0 radian or 0 degree. That is one quadrantal angle. Another one is, say this is your initial line and this is your terminal line, this one. Then the terminal line lies on the y-axis and the angular measure associated with that angle is 90 degrees or pi over 2 radian. That is a quadrantal angle. This is also a quadrantal angle. This one is also a quadrantal angle, and there are many others, okay, infinitely many. And you also have negative quadrantal angles. I mean angles whose measures are negative. For example, this clockwise rotation by 90 degree is a quadrantal angle, or the angle associated with this rotation is a quadrantal angle 2, whose angular measure is minus 90 degree or minus pi over 2 radian. Minus pi minus 3 pi over 2 minus 2 pi, or going in the anticlockwise sense, pi over 2 pi, 3 pi over 2 2 pi, then 5 pi over 2, all these things are quadrantal angles. And the reason that finding cosine and sine for quadrantal angles is easy, it's because for a quadrantal angle, the terminal side is either the positive x-axis or the positive y-axis, or the negative x-axis or the negative y-axis. As such, the point of intersection of the terminal side is with the circle is either A or B or C or D. Accordingly, we will have the values that can be written here of some of the quadrantal angles. They are cosine and sine values. And now you will see that it's really very easy. In fact, easier than what we previously got in school. Now also we are in school, but at a higher standard. Let us start with 0 radian. Cos 0. According to the school definition, it is 1. It should be 1, we already know that. But now you will see, and now you will realize why this new definition is in fact an extension of the existing definition. What is 0? The angular measure 0 is corresponding to the terminal side, which is the positive x-axis itself. So the point of intersection of that ray with the circle is the point A. So cos 0 by our definition should be 1 and sin 0 should be 0. Yes, it's matching with our old values. And in the old definition, we really somewhat struggled to make sense of these values in terms of right angle triangle, because we do not really get a right angle triangle, strictly speaking, in that case. Okay, next. Say next we consider this quadrantal angle, pi over 2 radian. In this case, the terminal ray is this, which intersects the unit circle at B. So, cos pi over 2 should be the x coordinate of that point, 0. And sin pi over 2 should be the y coordinate, 1. Do you see how it is easy it is? How much easier it is than the previous right angle triangle definition. Let us go beyond this. Say, next we consider pi, 2 pi over 2's. Then the terminal side is the negative x-axis and the point of intersection this time is C. So, cos pi should be the x coordinate of this point, that is minus 1. And sin pi is 0, because that is the y coordinate. We can go even beyond that to this angle, 3 pi over 2. Now the point of intersection is D, because the terminal side is the negative y-axis. So, cos 3 pi over 2 should be the x coordinate of D, which is 0. And sin 3 pi over 2 should be the y coordinate of D, which is minus 1. So, we see new things here. Because we have exceeded pi over 2 and we have got these higher angle values, we have gone beyond the old school definition. And that is why sometimes we are also getting negative values, which in school definition is not possible, because in school definition we know that this sine, cosine, tan, whatever else there is, all of these are ratios of side lengths. So how can such a ratio be negative if you are dividing a length by another? Here, however, that we have extended that, and now negative values are also appearing naturally. Now, if one makes a complete revolution, one then gets the angle 2 pi, 4 of these pi over 2's, so 2 pi, and the corresponding values will be, let me write here, cos 2 pi, again we have got back the point A as our point of intersection. So cos 2 pi is 1 and sin 2 pi is 0. So there is no difference between these two values and these two values, although the angles, that is the inputs of these functions, are different. 0, here you have 2 pi, but the values are the same. Okay. If you look at negative angles, I have kind of made this a mess, no? But I need the figure. So let me just erase parts of it. Now, if one thinks of negative angles, say negative quadrantal angles, such angles are also there, say minus pi over 2. If you think of minus pi over 2, then you are thinking of clockwise rotation by an amount pi over 2 radian or 90 degree. Then the terminal side becomes this, again the negative y-axis. So the point of intersection is D, and as such we have cos minus pi over 2 is the x coordinate, again same, I mean just we are applying the definition, 0 and sine minus pi over 2 is minus 1. Okay. If you go beyond this, then let's see one more value, minus pi, okay, cos minus pi. Now the terminal line is the negative x-axis. So the point of intersection of that line with the circle is C. So cos minus pi will be the x coordinate, that is minus 1, and sine minus pi is 0. Okay, so we have gathered quite a few values. Now these are of course not the only angles, there are infinitely many angles in between these possibilities and beyond these possibilities also. And accordingly we also have the various values of sin x and cos x, right, for depending on what x is. But just from these values you can see something about these functions, sin and cos. The first thing you notice is that values repeat. For example, you have got cos 2 pi 1 and cos 0 is also 1. Now cos 0 is 1 because the terminal ray is this and this is the point of intersection. If one makes one complete revolution, then the terminal ray comes back to that position itself. And so, obviously by our definition the values are not going to change. And that is why cos 0 is 1, cos 2 pi is also 1, cos 2 pi 4 pi is also 1, 6 pi is also 1, 8 pi is also 1. All these things are true and are going to be 1. In other words, the values of cosine, at least for this angle, gets repeated after regular intervals. Regular intervals means after intervals of length 2 pi. This language may be a little confusing right now, but we will make it clear afterwards, okay. Now, without being too specific, you can just simply imagine that the cosine values keep repeating. The sine values also keep repeating. That's because the definition is just like that, so that it makes the values repeat. The angles can be of any value, but since you have only these options available for the terminal ray to be, okay. So the terminal ray position itself gets repeated, that's why the values get repeated. And this repeating nature of the values is captured in something called the periodicity of trigonometric functions. That values repeat after regular intervals of time. Not time, but regular intervals of the input. That is one observation, okay, about which we are going to discuss much more later on. Right now, let us see something else also. What else do we see from these values? You see that we have considered positive inputs and a few two negative inputs as well. When it comes to the cosine value, the negative sign of the input has not actually changed anything. Cos pi is -1, cos minus pi is also -1. Is this true in general? Is cos minus x the same as cos x? Yes, it is true. We will see why. Not right now, but this is another observation. However, that is not the case with the sine function. Sine pi over 2 is 1, whereas sine minus pi over 2 is -1. It seems like when we change the sign of the input, the sign of the output also gets changed when we are talking about the sine function values. That is also in general true. Sine of minus x is equal to minus sine x. So these are some properties that we will see later on. Okay. However, let us next see something else. What should I see next? Should we see the sign pattern of these functions next, or should we see that this general definition includes in it the original old definition? Let us see the sign pattern first. Previously, in our old definition, there was no possibility of having any sign other than positive. Of course, you get zero values sometimes, but we did not have any negative sign or anything. Right now, however, we have negative outputs. So, one can ask about when these negative values or positive values appear. Because everything has been defined in terms of x and y coordinates, so we already know the answer, kind of. We just need to see what it is. So this is let me draw another system of axes. alright, and the circle is also there, okay, I am not drawing it again. Now everything is going to depend on where the terminal ray lies or terminal line lies. So if the terminal line lies in the first quadrant, say this is your terminal line, then it's going to intersect the circle at some point here. How far that point will be from O you already know, at a unit distance. But that's not the point. The point here is that the coordinates of this point, A and B, are both positive, obviously, because the point lies in the first quadrant. And that is why cos x is also positive because it is A, and sin x is also positive, right? If on the other hand your terminal line lies in the second quadrant, then its point of intersection with that unit circle also lies in the second quadrant. Again, this is A and B. This time, however, A is negative but B is positive. A is negative because we have come to the left of the y-axis, but B stays positive because we are above the x-axis. So this time cos x is negative but sin x is positive. If you are in the third quadrant, say, then both A and B are negative, and that's why cos and sin are both negative in the third quadrant. In the fourth quadrant, however, A is positive but B is negative. So now cos is positive but sin is negative. There is in fact a rule also which lets you remember when these functions are negative and when they are positive. Some ASTC something. I do not really like this kind of memorization techniques. Okay, if you can see this simply and this quickly, why do we have to remember such rules which themselves are easy to be forgotten, right? So these are the sign patterns of cosine and sine. In the first quadrant, both are positive. In the second quadrant, cos is negative, sine is positive. In the third quadrant, both are negative. In the fourth quadrant, cos is positive but sine is negative. Also, in all these things, you may forget one important thing. Cos is the x coordinate and sine is the y coordinate. Do not switch this, okay? Then everything will fall apart. Alright. Now, next we want to see that our old definition actually is included in this new definition. We get the old definition in the case when our angle is an acute angle. That means it will lie in the first quadrant. So let me draw such an angle. Now this is not the terminal ray, but this is the terminal ray. Okay, here somewhere it looks like a 30-degree angle or something, but this is a general angle. And this is the point P, whose coordinates are A, B. Okay, to declutter this space, let me just wrap these things off. Forget about these points and everything. We now only have the point P whose coordinates are A, B. So what we do, we drop a perpendicular from P on the x-axis. That perpendicular, say it has the foot of the perpendicular is say q. Okay. Then what is cos x? Of course, by our new definition, cos x is just a and sin x is just b. However, now this is our x. Because we have got back the old right angle triangle case, so we can use the school definition also to find out cos x and sin x. By the way, this OQ is A and PQ is B. And there is no problem with this because A and B are both positive, so they indeed are lengths. But if you go to some other quadrant, then you have to be careful with the signs of the coordinates. If you use that type of coordinate to write length, you have to make sure that you are writing a positive number. Okay. Here, however, this length is A and this length is B. So, according to the old definition, what should be cos x? Cos x should be OQ divided by OP. OQ is A and what is OP? OP is the radius of the circle. Since it's a unit circle, so it is 1. So you see that you are in fact getting A. Similarly, sin x is, by our school definition, PQ divided by OP. So we get B. This way we see that the new definition is more general than the old definition in the sense that it contains the old definition as a part of it. Alright. And now finally, before we end our discussion tonight, let's see one important thing. When do cos x and sin x become 0? That thing. Okay, so we can now get rid of these things. Will it be nice if we just use a new figure? So this is our unit circle, same things, x-axis, y-axis, everything. What is cos x? Cos x is the x coordinate. For the x coordinate to be 0, the point should lie on the y-axis. Any point whose x coordinate is 0 lies on the y-axis, and conversely, any point which lies on the y-axis must have its x coordinate 0. It's both ways. But the points we are talking about are the points of intersection of the terminal line and the circle. And that kind of point for us, now there are only two options. Either you have this point or you have this point. In other words, your terminal ray should either be the positive y-axis or the negative y-axis. These are the only two possibilities in which that the x coordinate of those points will be 0. Fine, but the terminal ray being this or this corresponds to many angles. Which angles? That we have to figure out. One of those angles, of course, is pi over 2. So when your x is pi over 2, then cosine is 0. Another such angle is 3 pi over 2. Another such angle is pi over 2, pi over 2, pi over 2, pi over 2, 4 of them and one more, that is 5 pi over 2. So if we start writing these angles, one of them is pi over 2, then we have got 3 pi over 2, 5 pi over 2. Then if you take 2 more, you will get 7 pi over 2. Then if you go even beyond that, 9 pi over 2 and so on. You see the pattern clearly. These are all odd integer multiples of pi over 2. And not just positive angles, negative angles too. Instead of going this way, you could have gone this way also, minus pi over 2. Then your terminal line is, the very first time your terminal line is this, the negative y-axis. So the point of intersection again has its x coordinate 0, that means cosine is 0. So minus pi over 2 is also an option. But then if you take 3 of minus pi over 2's, you get this point of intersection. Again you get cosine 0. So minus 3 pi over 2, minus 5 pi over 2, and so on. And these are the only possibilities in which cosine will be 0. And that is why from all this we get this conclusion that cos x is equal to, I can write on this side now. Cos x is equal to 0 if and only if x is an odd multiple of pi over 2. How do you write an odd integer? An odd integer looks like this, 2n plus 1, where n itself is any integer, n belongs to the set of integers. Cos x is 0 for precisely these values of x. The values are infinite in number, but these are the only values when cos x becomes 0. Sin x on the other hand becomes 0 when sin x is the y coordinate, and y coordinate becomes 0 only on the x axis. So the relevant points here are this and this. And what are the corresponding angles now? To get these angles, we go through a similar argument. One of the angles is 0 radian. In that case, this itself is the terminal ray. Now, if you start rotating in the anticlockwise sense, after this, you come to this position, and that corresponds to the angular measure pi radian. So you get pi, 0 pi, and then again if you have to go back to that position, you have to add another pi, that is 2 pi, and if you continue this, you will get the other values at which sine will become 0. But you can do this by going in the clockwise sense also, and that will further give you these other angles. These are precisely the angles at which the sine function will become 0. And these are all multiples of pi. Not even, not odd, simply multiples of pi. Well, actually you can view this as multiples of pi over 2 also. Then you will be looking at even multiples of pi over 2. But because 2 and 2 can be cancelled, so this ultimately become multiples of pi. And that is why sin x is 0 if and only if x is equal to n pi, where n is an integer. So we now know precisely when sin x is 0 and cos x is 0, and using this information we can now define the other trigonometric functions, the remaining ones. Let's do that and end our discussion. In defining the other functions, which we are going to do with the help of sine and cosine, we will be considering ratios again, but not of side lengths, but of sine and cosine values. So we need to be careful with the denominator. We should not divide by 0. That's why we needed this. Tan x, what is the meaning of tan x? Tan x is defined to be equal to your usual sin x divided by cos x, where, well, and here you need to carefully discard those values of x for which cos x will become 0, that is these values. You are allowed to put any real number x here except these values, where x is not equal to pi over 2, where n is an integer. That is your tan x. Next, let us see, what shall we see? Say cot x, cotangent. This is cos x divided by sin x. That's what it means. Okay, this is its definition, where this time we do not want sin x to be 0, so we have to discard the multiples, integer multiples of pi, where x is not equal to n pi for all integers n. Next, say secant x. This is just the reciprocal of cos x. So again, here also we need this condition. X is not any odd multiple of pi over 2. Even multiples of pi over 2 are okay when you are dividing by cos, because that is not 0. And one more is there, cosecant. Some people write COSEC and some just write CSC, although this notation is not used in this book. This is the modern notation. This one is kind of old and outdated notation. This is because it takes more space to write now, so instead we can write CSC. This is just the reciprocal of sin x, but again you have to get rid of the values, these values, where sin x becomes 0, where x is not an integer multiple of pi. Okay, so now we know fully the general definitions of all these 6 trigonometric functions, where x can be any real number, provided that these conditions are also satisfied depending on what function we are talking about. And that's where our discussion ends for tonight. But before I leave though, I want to mention something. In this entire definition, which is obviously more general than our school definition, it's a geometric definition, right? A geometry in combination with algebra gives us the definition. Our old school definition was also a geometric definition. And the thing is that we can define these functions without using any geometry. We can define them analytically. What this word analytically means, I cannot tell you right now because we would be talking about things which are far beyond the scope of this text. But just know that there are other and better ways of defining these functions which do not use any geometry. But of course, those new definitions, when you apply them to the familiar geometric situation, it turns out that you actually get these functions only. The advantage of that other definition, which is not geometric in nature, is that you can extend even them to calculate things like this. Cosine and sine of general complex numbers can also be defined, not just real numbers. This, however, does not have any geometric counterpart. So this is an extension of even this definition. We won't need this in this book, okay? So don't worry about it right now. So the thing is now is that we know all these functions in the most general sense that we can possibly have now. And the next thing we will do in the next trigonometry video is that we realize that these functions are now functions, okay, not merely ratios, where you have an input and you are getting an output. So naturally the question arises as to what their domains and ranges are. So we will be talking about that in the next video, and we will also see something about how the graphs of these functions look. And then the exercise problems will start. So that's just it for tonight. And what do we have tomorrow? I think tomorrow we have field theory. In field theory we have already completed one section. I think the last section is there of Galva theory. So we will start that tomorrow. So that's just it. So see you tomorrow. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.